This is a Super Saiyan. This is what is known as a Super Saiyan that has ascended past a Super Saiyan. And this is to go even further beyond!
Horror story time. So, you could read off your animation tree, you set some sexy modifiers up, you can use single animation, you can mix a spectrum of directions into one animation, and you can even mix between those two approaches smoothly. Let's demonstrate our ability to change between animation and motion spectra with these two locomotion packages, Combat Walk and Jog. Both have similar structure of having 8 mixable animations for start, cycle and stop, and one animation that stands idle. I'm sure I set everything right. Why do I get an artifact when going from stops to idle? Both behaviors have this strange ick movement that isn't present in any of the animations. Let's check the last frame of Combat Walk stop animation and assert that it doesn't have any legs slide to the center. Testing again. Strangely enough, the Combat Walk actually fixed itself. Jog is still broken. I haven't changed any code, but let's check this with Jog stop. Now Jog is fixed, but Combat Walk is broken again. The only parameter that was changed between launches is the animation that is selected in the animation player. Let's do something radical and set the observed animation to something like sliding. Now everything is broken, but at least we can clearly deduce what is happening. For a small period of time, specifically when we mix between two different modifiers, something mixes in a tiny little fraction of the slide animation data into our skeleton. Somehow, this animation that is just chosen in the editor on an animation player that is not even active impacts the result of your animation modifier's output. Rest in peace for all the brain cells that could be lost in the process, but the reason is super obvious if you know how modifiers work. Moreover, Godot developers tried to tell us about this behavior caveat in their blog post about skeleton modifier design. At the beginning of the update process, it stores the pose before the modification process temporarily. When the modification process is complete and applied to the skin, the pose is rolled back to the temporarily stored pose. In other words, at the end of each frame, all the work your modifiers did during the frame is discarded. The pose of the skeleton then reverses to some default value it had before any of the modifiers were applied. And even a scene that doesn't work with skeleton and doesn't have an active animation player has this default pose value that is equal to the original pose the skeleton had on the project start, just because it's saved as is when the scene is saved. If you use your modifiers as intended and only apply them as some post-effects work on top of existing animation tree or animation player, this probably won't disrupt your process much. But if you are some crazy Ivan that wants to create a full animation framework with modifiers alone, that needs to be worked around. And the easiest way to do that is just to save your modifiers work at the end of the frame. Look, my animation system is placed between two modifiers, one is always the first to be processed and another is always the last. They have other jobs, for example, first modifier is the meta modifier from the original video. It manages the other modifier's active status depending on the influence to save us computation costs. And the last modifier doubles up as the debug modifier if I need to draw something. But the most important thing they do is they work in pair, because the last modifier is, well, last. After it is processed, the frame ends discarding our delta pose. So what we do is we just snapshot the pose to preserve this data, and then in the beginning of the next frame the first modifier takes this snapshot and sets the pose of the skeleton as it says. This cycle makes it so when first actually animating modifier is processed, the skeleton's default pose is the state we left our skeleton in the last frame. Let me uncomment this line, and problem is fixed. The next thing I want to talk about is a trick that allows you to gain a nice performance boost. This episode is also a natural advertisement for my Discord server, because the technology is not invented by me. It was shown to us all by this gigabrain nicknamed 888. The core of the computation cost we cut is this little function called findTrack. It takes track's name and type and returns the index of the track with such name and type. Track IDs are indexes in an array, and track's name is an attribute of an element. And to find an element of an array by modify its attribute, one must traverse the array, asking every single element about its attributes, until the needed one is found. This takes O from N operations and really slows us down if we call this fuckton of times. Well, anytime you want to cut the cost of a fuckton of searches, use hashmap. Simple as. Hashmap has O from 1 search difficulty and you will save a lot of time while paying for it a minuscule cost of having this hashmap in the memory and generating it anew once in a while. This was what 888 suggested. Look, in the transition call, the script takes the newly requested animation and does a single run of baking its bone to track map. And that works perfectly, don't be scared of this performance cost on transition. From 1 per frame perspective, transitions are rare and you will barely notice them. However, if you wish, you can squeeze out even this drop. We need to generate a new bone to track map on transitions only if these maps come out different from time to time. If all your animations have strictly identical structure, you will only need one map that you bake outside of runtime. And the neat part is that we can actually force Godot to have identically composed animations. When you import a set as an animation, Godot tries to help you and ignores the tracks that don't do anything for your animation. This additional processing can be turned off by this checkbox. If done, your assets will get a lot of garbage tracks that don't really do anything. However, if you made your animations on one skeleton, they will be universally equal. I don't fear additional small cost of assets at all, we almost don't lose on that. I also don't fear the bloated tracks list because I don't change anything by hands in my animations. This whole area is basically dead interface for me anyways. So I re-imported all my animations as equal lists and I use a single bone to track map that I baked once with a small helper script. This trick heavily cuts the track searching cost of your modifier's work. Therefore, the simpler is your skeleton, the bigger the performance boost you get will be. Our skeleton is huge and complex, and it gained about x 1.5 to 1.7 boost. Mixer skeleton is simpler and it becomes about 3 times faster, and the further you simplify your character, the bigger profit you will get. If you ask me, I don't even know why the original animation searches linear search at the first place instead of being powered by hashmap all the way. I generally abstain from shitting on people who support something huge written in C++. There probably is a reason somewhere, but I don't get it. Maybe at the time it was written, people didn't consider it being called several hundreds times per frame. The next micro tip is for people who want to split torso and legs. If you saw previous animation video, you remember the proposal to use classical animation player to play settings animation that have modifiers influences as changed parameters. Well, I'm glad to report you that the approach is up and well and shows effectiveness, etc. However, if you will try to create a robust torso leg system, you will run into the problem of multiplying settings amount. To combat it, don't hesitate to split your settings player into 2 as well. One plays torso settings and the other one plays legs settings. They are completely independent of each other and are managed in parallel by their correspondent behaviors and actions. This is not cringe, it works, it is fast and comfortable to code around. Another tip for torso-legs splitting is on syncing your torso and legs smoothly if desynced. Imagine you have been jogging, then at a random moment you played some jog legs based animation on your torso while leaving jog legs as is. When your torso animation ends, torso must transition back to its jogging animation. But if you'll do it in a stupid way, your torso will be played from animation start, while your legs are running with some random progress already. Look, my default jog is balanced and character moves its right shoulder forward when its left leg is moved forward. Then I eat some Dr. Livesey Walk pills, they take effect instantly, and now my character moves its right shoulder forward in sync with its right leg, what looks kinda clunky. To fix this behavior, you need to sync your torso animator to your legs animator when you enter jogging state. You can just teleport your torso animator into some progress, that is not a big deal, but for the next technology I need another magic trick of a similar but different nature, and here I have a nuclear solution in form of this sync and follow method. Let's start from the follow part. It is represented here by this line. Each animator has this small instrument installed here. I have done it as 2 fields for syntactic sugar purposes, hasFollower and follower. Follower is an optional field that must contain another modifier of this exact type, i.e. simple animator can be followed only by simple animator and locomotion mixer can be followed only by locomotion mixer. And all it does, it subscribes another modifier to our transitions. When we get a transition request, we do all our stuff stuff and echo this exact transition request to our follower. What it achieves for me is it allows me to subscribe my torso animations to my legs animations logic if I need to. For example, my locomotion states are done in this way now. These behaviors that represent just torso with some directional movement mode are now actionless behaviors. They don't have their own animation logic. Instead, on enter state, they just tell, okay, all the nuanced stuff about starts, cycles, stops, pivots, idles, all that is already covered by my legs logic, so I won't do it again. I will just copycat my legs animator settings into my torso animating settings. And the sync part is really similar to transition request, but instead of an actual request, we take another modifier of our type as an argument and copy its field's content. Remember this tag? It will help us in the future. And now we are going into the last chapter with the most interesting and hard content. We get another modifier. It is called Smart Torso Overlay and it is able to give us this result for our block animation, using a locomotion state as a base layer and an animation of this blocking pose as a mixed-in asset. It is also customizable as fuck, can power sexy secondary motions and skew any torso animation to any legs animation, as it is immune to pelvis direction conflicts. Speaking of such conflicts, why do we even bother? What's the problem with just having a blocking animation and play it in on the torso? Well, that's what will happen if you do. It happens because the original legs of blocking animation have this pelvis that looks to the side, and the shoulders behave as if it was the case. However, when transplanted onto legs animation with different pelvis position, shoulders don't adjust and break the animation. And we want to use this one blocking animation overlay and slap it into any legs we want to and stay flexible during development, instead of being forced to create a set-in-stone blocking asset per legs behavior that asset must be played on. To achieve this, we need to smoothly blend our bone chains from one animation onto another. Here's the scheme. We have here a green human that will represent the underlying animation. We have a red human that represents the overlay, and here we have this thing. It's not a figure, but a hole in shape of a human, just like a first love. First thing first, everything from pelvis and below is green, as it is taken from the underlying layer. Then at some point, probably on the shoulder line, we want a strict copy of our blocking asset, so it is colored as red. Then, to sew this thing together, we take our spine bones and gradually mix two animations together by starting as underlying pelvis and distributing the adjustment between the spine bones. Then we do even more interesting thing. Look, we have two different arms here. The left arm holds our shield. It is an important task. The arm has weight and both character and player are probably concentrated on this shield being lifted. So for left arm we want more of the original animation. However, we don't make it completely red to save some sexy secondary motion blended in from the underlying layer. On the other hand, right arm is not as important, neither for character nor for player. It just dangles around in the back and is somewhat relaxed. And because it is relaxed, we can allow it to be greener, to be more influenced by the base layer animation. Well, that's quite easy to do. However, I didn't tell all the truth. A tiny percentage of people who watch this video can understand this skeletal animation stuff on the fly, and right now they are sure that I'm a bullshit con artist. The thing is, if you just iterate over all bones and mix two animations together in this manner, you won't get the desired result. You will still get a variant of this botched configuration. This is because Godot's animation resource, and probably all animation resources from game engines, encode bone's rotation and position in its local coordinates. In other words, when a bone tells you it is oriented alongside y-axis, it doesn't mean that it's oriented vertical. It means that it's oriented alongside its parent. In other words, the fact that these shoulders look in this direction is not only dependent on the basis of the shoulder bone, it is also dependent on all previous bases in the spine chain. And this is the reason why this peculiar forward kinematics modifier returns results that can be misinterpreted as inverse kinematics effect. Unlike any other modifier, here we use bone's global pose instead of its local pose. You get it? At any given time, for any given bone, we ask skeleton on how it looks like right now relative to skeleton. This is just the skeleton.getBoneGlobalPose call, and it returns the result we achieved with all previous skeleton modifiers. Then we calculate how does this bone look in the original source of the overlay, also relative to the skeleton. And then we interpolate between those two global poses and set the result as our new global pose. That's the core of the algorithm. Now onto some implementation details. First of all, this modifier is costly. As a zero-step cost, I remind you that it is not used as a solo modifier. This is an overlay, so you add the cost of some underneath torso layer, probably local motion mixer. Then, as we work with global poses, we need to calculate them, and that's a big pain in the ass to do. In a vacuum, to get the global transform or basis of nth bone in the chain, you need to multiply local bases of all the chain bones from the very root up to your nth bone. Some chains, for example, from root to the tip of the finger, can be pretty damn long, and if done brutally, each time you add another bone, so that's a triangular structure. The sum is n by n divided by 2, so the operation cost is O from n square. To have an n square skeleton modifier is GG. That shit burns your processing times. The original proof of concept modifier was calculating the pose for 2 milliseconds alone. Luckily, one can choose to not be stupid. The basic way to optimize it is to reuse the previous bone global pose. Look, if I want the global pose of bone number 83, then I can just take the global pose of a bone number 82 and multiply it once by 83's local basis. And the parent bone is done at the exactly previous cycle step when we process a hierarchy. Well, ironically, this sole tech instantly improved the computation time from 2 milliseconds to 1 something, but I craved more. For a long time, I was haunted by the ID fixer to make bake animations work. Imagine a random animation. You get a request to interpolate it in some random time, and you need to find the 2 keyframes to do your interpolation. Like, that's a binary search. Not much, but something, and we do it for every bone, for every track, for every modifier, in every frame. However, there is a button down here that tells bake animations. What it does is it turns your animations into a strict keyframe per frame encoding. From data storing perspective, that's a nightmare. You spend several times more memory to encode the same animation with a god-awful amount of unneeded keyframes. However, if you guarantee that your animation keyframes stand on exactly equal timing windows, then you can skip interpolation frames search. You can just divide the interpolation time by the amount of frames in the second and then do some clamping and some edge cases dance around. And from there I sort of descended into the next solution madness. You see, for a long period of time I was a bit dissatisfied with Godot's animation API. I understand why they cut their pie this way. Skeletal animation is just a drop in the sea, and all what animation can offer must work for both 2D and 3D and to be powerful enough to work with half of the random engine parts. I mean, look at my own project. The default animation player can casually play and mix animation that change a float parameter of some custom node in the scene. This is really powerful, really flexible, and is really broad scaled. But with such broad-scaled solution, they are losing the sight of small things that might require tougher coupling. Imagine for a second that you live in a world where non-skeleton animation doesn't exist at all. Then look at this API. Animation doesn't work in bone terms, instead they have independent integer indices and track names that are not even equal to bone names. Animation stores rotation as quaternions, while skeleton is being mostly basis-based aside from one method. Where are transform tracks? If we don't want to make them, then where is an arc API call that is able to build and retrieve the transform with one line for user not to build their own from position and rotation each time? Why don't we have a switch here that allows us to process the animation as baked or not baked? Like, surely that will give at least some speed. Where is the half of the functional that works with global poses? Animation have only local pose data in them. With each such question, the whispers from my left shoulder became louder and louder. Why won't I make my own animation encoding resource with blackjack and transforms? There, in my domain of shooting myself in the leg, I will be king, and I will answer all those questions as I prefer. Well, you know me. The moment this thought was born in my head, I was basically sentenced to try this at least to see if I can make it possible. Behold, the skeletal animation resource. Currently, it is in an extremely raw state. I don't have my API polish, I only have it up and running. It is extremely similar to a standard animation resource, but it has a small subset of its functionality. And it is skeleton aware. Here I have the default stuff, animation name, length and looping mode. I have never used a bouncing loop, so I didn't include it. Then I have here two arrays for animation data. Local data is basically a standard animation, but instead of animation tracks IDs, we straight up use skeleton's bones IDs. And another twist is my animations are baked by default. I have strictly 60 FPS divisions. This allows me to have an array of like length multiplied by 60 indices, and in those arrays I store transform 3Ds directly. I don't break them into rotations and positions. And then, right below it, I have another data array duplicated. This is a tale old as time. I pay with memory and pre-processing to buy runtime computation. This array has exactly the same structure as local data, but it stores global transforms of bones. Global relative to skeleton because for bone this term is redefined for some reason, and the fact that I store all that allows me to work with skeleton modifiers that use global transforms with the same speed as if they were using local transforms. In the end, I was a bit dissatisfied with the base improvement. Relative to just catching bones to track maps, this new approach made my classic animation modifier from 20 to 30% faster and my locomotion mixer only 5 to 10% faster. Well, I hoped for more, but hey, don't you forget what pushed us here. Remember this guy who ate a whole millisecond from each frame post-optimization, thanks to global data usage, built-in caching, and baked animation structure. Now he looks like this. Moving back to it. I told everything about how does it work, but let's look again. We have current overlay and previous overlay to enable blending. We get original overlay's global rotation, we get current rotation of the skeleton, and we interpolate them with weight value we got from our weight map. This weight map is a resource. Currently it is pretty raw. I just have it exported to the modifier and it is static. It works because currently we have only one such overlay state in our system. In future, this weight map of course must not be a static export field, but an attribute of a state instead that you provide as an argument to the play function. But I am still very proud of how good it is. Essentially, this is a Godot implementation of this weighting picture from the theory overview, but instead of colors and skeletons, I have a 2D curve. Here I have 3 chains, spine and 2 arms. The chain is essentially an array of integers, and below I have a curve that defines weighting. Left side is chains start, i.e. hips for spine and shoulders for arms. Right side is chains ends, i.e. fingers for arms and head for the spine. And then, the higher the value, the more influence the overlay holds over the skeleton. Let's illustrate with spine. So, if I set everything to 1, then I have only the overlay and it looks botched and twisted, especially if I additionally rotate pelvis in the opposite direction. Then I set the start of the chain to 0 to have smooth blending from my pelvis, and to have some secondary motion in my shoulders, I set the end of the chain to only 0.5. This way, our shoulders are not static and tap into the underlying animation a little bit, creating an amazing impression of an actual living being moving. And all this beauty is powered by dragging some points in export field, for you or for your animator to abuse your assets with complete artistical freedom and being able to check out how they look directly in the runtime in this exact engine editor. Who is the 3D software now, huh? Usage. I see 2 big usages for this technology. First is a very flexible torso behavior customization design for different equipment. Let's consult the holy source. So you made yourself a standing, jogging and sprinting torsos for your character. You also have some weapons here in the scene. When you are at the stage of early prototype, these things are thin as the ice I'm standing on continuing to live in Russia, but one day you will need to add content including different weapons. Then if you have such an overlaying technology, your life is easy as fuck. Look, you can have bazillion different weapons. Each weapon has an attribute that documents its overlaying animation names, one for standing, one for jogging, one for sprinting, probably some other like blocking, sheathing, unsheathing, etc. Then you don't duplicate any states. You have exactly one jog, one sprint, one block, etc. And what they do is they overlay the before mentioned torso animation depending on the weapon your character holds. And just like that, without over-defining anything, practically by just having the needed assets, you get yourself a sexy looking game that have individual torso animations for each motion plus weapon combination. Second big usage is overlaying of some animations that do help you to immerse players into the world, but don't have any state beneath them. For example, stateless hit reactions. If your character can suffer some direct bow arrow hit without lifting a shield, but you don't want to hard stun them like Dark Souls staggers, you can play the hit reaction animation on top of the skeleton. This way you successfully communicate your narrative to your players, you tell them that character is hurt, but you don't take any behavior control from them, and don't underestimate how important hit impacts are for your game's immersiveness. You can have all the graphics in the world, but if your hits don't have impact, players' monkey brain is instantly reminded that they are playing some fake plastic dolls. Similarly, you can have mood modifiers animations installed that work depending on some resources or statuses. For example, you can make your character's posture progressively more curved depending on its health amount, or you can make them slightly tight and shaky to signal that they are traversing a cold region. You can even implement a complex mechanic of being wavy drunk if you are willing to go for such lengths. Also, remember that nuclear solution to make your torso animation pipeline hooked to your legs animation. This blocking state is where we milk it to its fullest. My blocking torso behavior can utilize two different legs behaviors: combat walk as default and jogging if you input the sprint modifier as well. Those modes have all their starts, cycles and stops animations. Plus I also want my block to have a start, stop and end animation. To escape thinking of what exact underlying locomotion animation must my torso play beneath that block and pose overlay, I use that sync and follow instruction and just don't give a fuck. My legs are smart enough to decide on how to move, and here I only think of how do I overlay the pose and what is the difference between block stages. Thanks for watching. If you can, please overwrite your right hand animation by the one that likes the video and subscribes to the channel.